important this region of convergence is. Let's have the signal x of t is equal to minus e to the minus at u of minus t. As you see, many of these indices are now negated. When you take the Laplace transform of that in terms of the definition from this integration, that is equal to, with a minus sign, from minus infinity to infinity, e to the minus at e to the minus st u of minus t dt. And this u of minus t imposes this thing to start from minus infinity and go to 0 this time. And e to the, in minus parentheses, a plus s t again dt. And you may believe it or not, it gives us this expression, 1 over a plus s. Although I have erased the previous answer, if you check your notes, you will see that it's the same answer as the previous example. So what's wrong here? The transformations are required to be one-to-one, because for every transform we must have an inverse transform. If the Laplace transform of x of t is equal to x of s, in other words, then the inverse Laplace transform of x of s must be x of t. But in this example, things don't seem very invertible. There is something wrong here. We have the same. So what is the difference? What may help us to differentiate between this signal's Laplace transform a plus s, 1 over a plus s, or the previous signal's Laplace transform? What was the previous signal? It was e to the minus at u of t. It was that. And its Laplace transform was still 1 over s plus a, or a plus s, whatever. So they are the same things. The only difference between the two is in terms of the region of convergence is in region of convergence. The Laplace transform expression is the same, but the region of convergence of this new Laplace transform is different. Let's try to understand, motivate why the region of convergence is different, or what is a reasonable a value for our case. What was a reasonable a value for the previous thing, for the existence of the Fourier transform, for example? It was when a is greater than 0. When a is greater than 0, then e to the minus at will be a decaying exponential. But if you take a to be greater than 0 here, this will be again a decaying exponential, same, but look at this, u of minus t. So it's a decaying exponential. There's a minus sign. Let's forget about that. Let's only think of the magnitudes. It's a decaying exponential, but we are considering this decaying exponential from minus infinity to 0 part. And over there, it blows as time goes to minus infinity. So this a is less than 0, sorry, a is greater than 0 case is problematic. A is greater than 0 in this curve corresponds to this kind of a thing, and because of this u of minus t, it's not u of t anymore. It's from minus infinity to 0, and over there it is a diverging signal. So this integral, in other words, this integration is not valid for such a case. When a is greater than 0, the integral diverges, in other words. This integration, or this integral, converges in the opposite case, when or if the real part of s plus a is less than 0, it converges. It's not when the real part of s plus a is greater than 0. It's a different condition for the convergence of this integral. If real part of s plus a is less than 0, or real part of s is less than minus a. So this is our new region of convergence for this. When you plot it on the Laplace plane or the S plane, it happens to be like this. Let's again assume a is equal to 3. If a is equal to 3, then minus 3 is somewhere here again, and it's not included, and real part of s is less than that. Where is it? It's here. This is the region of convergence, and it's quite different from the previous plot. In the previous plot, the region of convergence was real part of s is greater than minus a. This time it is less than minus a. And only by knowing this, if you have this, and of course if you have the Laplace transform expression, using these two, it is possible to find the time domain signal, which means when I take the inverse Laplace transform, I will get a distinct or unique x of t. If I give you this Laplace transform and say that real part of s is greater than minus a, then what will be the time domain signal? So I am saying that x of s is equal to 1 over s plus a, and real part of s is greater than minus a. And the question is, what is x of t? And the answer is, x of t is equal to e to the minus at u of t. This is the inverse Laplace transform, the first example. If I ask you in the alternative way, x of s is equal to 1 over s plus a, and real part of s is less than minus a, which corresponds to the new question, by the way, then the question is, what is x of t? X of t is minus e to the minus at u of minus t. Okay? So how do you distinguish between the choice of these two? You have to choose according to the region of convergence. They both correspond to the same Laplace transform. The x of s parts are the same. Now there is a very nice and easy and quick way of finding this solution or this solution with respect to the region of convergence. And that is the extent of the region of convergence. If the region of convergence is towards the right, if it's to the right hand side of the plane, you cut the plane, and from that cutting point, if it's towards the right hand side, then your signal is also right hand sided. Look at that. E to the minus at u of t. U of t is right hand sided. If your region of convergence is like this, if it is extending to the left hand side, like this one, then your signal is also left hand sided. U of minus t. U of minus t is a left hand sided signal. Okay, that's how you select it. That's how you choose between the two. Now, another example. Of course, before these examples, it may be critical also to directly by looking at this x of s, the Laplace transform expression, you should expect some region of convergences. And those region of convergences come from where? So let's not start a new example, but let's talk a little bit about the region of convergence limits or bounds how do we determine the bounds? With, of course, when you take a look at the signal itself, for example, when you take a look at this one, or when you take a look at this previous example, when we take this integral of x of s, we see that in order for this integral to converge, the exponent must be in the decaying side, and from there we come up with an expression. We come up with this one. But it's too difficult. And in some cases, the students or the scientists can get confused under which circumstance this one converges or diverges. Left-hand sided, right-hand sided, it's a problem. Okay, there's a problem here. How can we determine quickly and efficiently the region of convergence? There is one very easy way to do that. And that is obtained after you take the Laplace transform. This is the Laplace transform, right? We are assuming that this thing converges, and this is the integral that we get. By looking at this integral, you immediately see one very important point of S. That is also known as the root of the denominator. This denominator is a polynomial in S. The parameter of the polynomial is S. It's a first order polynomial. It's not quadratic, it's first order. So what is the root of this polynomial? S is equal to minus a. You have to just equate the denominator to be 0 and solve the equation. So S is equal to minus a is the root of the denominator. That S is equal to minus a, which is the root of the denominator, is indicated with a cross, and you call it to be a pole. Okay, you immediately put it like this, and from there on your solutions are quite reduced. It's either the region of convergence is automatically either to the right of the pole or to the left of the pole. That's the only choice, because the region of convergence cannot include, sorry, let me write it like this. Region of convergence cannot include a pole. That's a necessary condition. So if there is a pole at minus 3, then the region of convergence cannot be from minus infinity to 1, for example. Why? Because if that is your region of convergence, then minus, what is this? Minus 3, there is a pole. This pole cannot be inside the region of convergence. Where can it be? It can only be at the bound. So this is your boundary. Is it to the left or to the right of the pole? How do you decide? You decide by looking at your signal. Is the signal left-hand sided or right-hand sided? This one is left-hand sided, so the region of convergence is to the left of the pole. Simple. And how do you indicate it? You say real part of S is less than minus a, because at minus a there is a pole. A plus S is the polynomial. Its root is S is equal to minus a. At S is equal to, real part of S is equal to minus a, there is a pole. And you say it is to the left of minus a, because the signal is left-hand sided. Is this clear? Very simple. Otherwise, if you think of how to make this integral to converge and conclude with something like this, this is difficult. Don't do that. Just find this, indicate the pole. If the signal is left-hand sided, the region of convergence is to the left. If it is right-hand sided, the region of convergence is to the right. By the way, for this question, for example, the first example, again the pole is at a minus a, S is equal to minus a, and the signal is right-hand sided, because the real part of S is greater than minus a is to the right-hand side of the region of convergence. So you choose this answer. Or if you have this question, you choose this region of convergence. If you have this region of convergence, you choose this answer as the inverse transform. Okay? Now, this is, however, something quite important. The region of convergence cannot include a pole. And in some cases, the poles may be multiple. In other words, the Laplace transform may have a higher degree polynomial in the denominator, then there will be multiple poles. And furthermore, when they become quadratic or third order, the roots may even be complex. Then what would happen if you have complex poles or multiple poles? You shouldn't confuse yourselves a lot. You just need to indicate the positions of those poles. Now let's see an example of a complex pole. Which is this: x of t is equal to 3e to the minus 2t u of t. So this is for the this is an example of the multiple poles, by the way. It's not a complex pole example. 2 to the minus 2 times e to the minus t u of t. All right. So this is your signal. The signal has two exponentials. Both of them are decaying exponentials, by the way. This one is a decaying exponential and it is right-hand sided. This one is a decaying exponential and it is again right-hand sided. So what's the Laplace transform? The Laplace transform of this part we already found. We know how to solve such questions. It is 3 times 1 over s plus 2, or 3 over s plus 2, and there's a minus sign, and this is 2 over s plus 1, simple. Okay, so this is the Laplace transform. Let's try to combine them. Although in this particular form it's easier to analyze and proceed further, when you equate the denominators and apply the necessary algebra, you will get this: s square plus 3s plus 2. But I'm giving you this expression because in the question I may ask you this way as well. I can say that this is x of s, and I may ask you what is the inverse Laplace transform, and then you have to tell me this minus this, for example. So from here you must first separate into 2, and the separation into 2 is obtained by finding the roots, the first order roots. So how many roots does it have? It has 2 roots. The first root is root 1, s1 is equal to minus 2, and the second root, s2, is equal to minus 1. Let's draw the s-plane. This is minus 1. This is minus 2. This is the real axis, and this is the imaginary axis. And these are real numbers, by the way, so these roots or poles are on the real axis. But if they are complex, they may be somewhere else on this plane. So these two are the 2 roots. What is the region of convergence? This is the Laplace transform, your answer. So out of 10 points, you get 5 points from here. For the other 5 points, you have to tell me the region of convergence. Where is it? Between. Why do you say between? No. I would say that the region of convergence is, for the first part, it is real part of s greater than minus 2, and for the other one it is real part of s greater than minus 1. Let's call this region region 1, the other region region 2. What is the region of convergence for the both? It is the intersection. So the region of convergence, let's call it R, is equal to R1 intersection R2. Where is it? Greater than minus 2 intersection with greater than minus 1. Yeah, it's greater than minus 1 is the intersection. Let's draw an imaginary boundary here, bound, and to the right hand side. Intersection with another imaginary bound here to the right hand side. The intersection is, of course, here. to the right of minus 1. So the combination is real part of S is greater than minus 1. This is the answer. This is the correct answer. And now you have to ask yourselves the harder thing. I'm showing the easy stuff, and the harder stuff I'm reserving for the exam, of course. In the exam, I must ask in a complicated manner to make life more difficult. For example, I must ask you like this. This is x of s. And this is the region of convergence. What is the signal? What is x of t? What are you supposed to do? Let's assume that you were able to split this thing into two additive components like this. Let's assume that you managed to do that, which is an issue by itself. It's not very easy to split like this. But suppose you did. After you did that, from here you have two choices. Do you agree? For the signal, for the corresponding signal. Two choices. What are those choices? One of them is the right-hand sided solution. The other one is the left-hand sided solution. Okay? For every first order system you have two choices. Now will you choose the right-hand sided solution or the left-hand sided solution? For that you have to take a look at the pole of it, minus 2. And is the original region of convergence towards the right of it or towards the left of it? It's towards the right of it. It's even more than towards the right of it. It's not only towards the right of minus 2, it is to the right of minus 1. But naturally, you must choose the right-hand sided solution for this one, which is this. And then you have this. Again, there are two choices, and you have to choose the right-hand sided solution again, which is this. Now let me ask you alternative answers or alternative questions. The same x of s is given. Let me rewrite it. It's equal to s minus 1 over s squared plus 3s plus 2. Now let's make the life a little bit complicated, and let's assume in between, because that's also a possible solution, by the way. So the region of convergence is defined as the real part of s is greater than minus 2 but less than minus 1. A new region of convergence, or in terms of the plot, this is minus 2, this is minus 1. The region of convergence is in between. This was the first answer that you gave me, right? Now let's assume that it's true. This is the region of convergence. What is the time domain signal? How will you find it? From here, first you need to split it into the first order components, s plus 2 minus 2 over s plus 1. Okay? This one, is it to the right of minus 2 or to the left of minus 2? It's to the right of minus 2. Intersection with to the left of minus 1. The intersection is here. So the right-hand side, the solution is already there. It is 3 e to the minus 2t u of t. All right. Now let's take this. Will it be the left-hand side or the right-hand sided solution? The left-hand side, because it's to the left of minus 1. What's the left-hand sided solution to that? There is already a minus. From the left-hand sided solution, we need another minus, which would make a plus. 2 times e to the minus t u of minus t, exactly. So you know how to do it, right? This is the solution. This is the answer to this question. Can you formulate an extra question from the same starting point? Yeah. Let's assume that the real part of S is less than minus 2 to the left. This is a possible intersection. It means that it is to the left of minus 1 and it is also to the left of minus 2. And the intersection is to the left of minus 2. So what is x of t? Then this one will correspond to a left-hand sided solution, which is minus 3 e to the minus 2t u of minus t. And for the other one, it's like this one, plus 2 e to the minus t u of minus t. Agree? Another possibility still exists. What is that? The region of convergence is an empty set. What does it mean? Well, if the region of, that's a moronic question, because if the region of convergence doesn't exist, then it means the Laplace transform doesn't exist. So which inverse Laplace transform I'm talking about? There is no Laplace transform. It doesn't converge anywhere. It doesn't exist. But let's think of a hypothetical situation here. For this, we can still find the answer if even if the region of convergence is empty set. Then it means, yeah, it is to the right of minus 1, intersection with to the left of minus 2. And their intersection is nowhere. And what is that? It is to the left of minus 2, which is this one, minus 3 e to the minus 2t u of t, sorry, u of minus t, minus 2 e to the minus t u of t. Now we come up with an interesting situation. It is saying that the Laplace transform of this x of t doesn't exist. Well, I said that Laplace transform is a larger set. It's a superset of Fourier transform. Even if you don't have a Fourier transform, you may have a Laplace transform. For instance, by the way, for this region of convergence, which corresponds to this signal, right? We found it to be this signal. What is the Fourier transform of that signal? Could be asked to you. And you have to give me the answer. What? What is the Fourier transform of this x of t? J omega minus 1 over minus omega squared plus 3 j omega plus 2. Wrong answer. Very close, but a wrong answer, because that is the Fourier transform of this signal, unfortunately. The Fourier transform of this signal is that one. But the Fourier transform of this signal, which is different, what is that? The answer should be given like this. This is the region of convergence. Does it include the case of sigma is equal to 0? Sigma is equal to 0 is, by the way, this j omega axis. So you must ask yourselves this. Does the region of convergence include the j omega axis? So let me write that question here. Does j omega axis, does region of convergence include the j omega axis? You must answer this question first. If the region of convergence, for example this one, does not include the j omega axis, then you're in trouble. It means the Fourier transform doesn't exist. So the answer should be the following. What's the Fourier transform? It doesn't exist. But for this one, is j omega axis included in the region of convergence? Yes, it is. It is inside the region of convergence. Therefore, you can safely replace all the s points with j omega. Sigma is equal to 0 means s is equal to j omega. Just put j omega here. That is your Fourier transform for this signal. For that signal, this one, the answer is j omega axis is not included in the region of convergence, so the Fourier transform doesn't exist. The Fourier transform of this final example doesn't exist either. Right? But it's even more than that. Even the Laplace transform doesn't exist for that. There is no region of convergence that is available to you. And why is it the case? I mean, can you try to visualize signals? How come the region of convergence doesn't exist? If you plot this, e to the minus 2t u of minus t, e to the minus 2t u of minus t, let's draw a small figure here. It is without the magnitudes, it is a very fastly growing towards the negative side. It's a decaying exponential, but because of u of minus t, we take it like this. The other one is e to the minus t u of t, which is a decaying exponential. So it looks like a normal shape which is decaying. So how come I'm unable to obtain a Laplace transform for that? The reason for that is that when I multiply this shape with an exponential, because that's what I do in the integral formula of Laplace transform, there is an e to the minus st multiplication and the dt. So I first multiply this with an exponential and then integrate from minus infinity to infinity. Now I am unable to find any exponential, decaying or increasing, whichever shape you may think of, which suppresses the left hand side and the right hand side. I am unable to find it. Because after the multiplication I am integrating. So the left hand side must be a decaying and the right hand side must also be a decaying exponential. And only then, when I integrate from minus infinity to infinity, I come up with a finite value. However, when I multiply this thing with any integral, any exponential, I cannot integrate from minus infinity to infinity. The opposite, on the other hand, is available, this one. What is this? It's e to the minus 2t u of t, so it's a strongly decaying exponential. See that? This one. And e to the minus t u of minus t is increasing towards the right hand side with a rate. But the rate of this one is smaller than the rate of this one. So, for example, when I multiply the whole thing, if I take it and multiply it by e to the 1.5t, for example, then this will suppress this one, the multiplication. I'm going to multiply it with this shape, in other words. This part multiplied by this part, the multiplication will be decaying still. And this part, right hand side, multiplied with this part, will still be decaying as well. So both parts will be decaying, and when I integrate, I come up with a finite value. For that, I recommend that you try to draw accurately, or in MATLAB, for example, try to draw and visualize why these are possible. So with an exponential factor of your choice between minus 2 and minus 1, which I chose to be 1.5, by the way, inside the region of convergence, when I multiply, I'm able to obtain a converging integral. But even without that consideration, it's something extra, I have to admit. The others are quite easy. You have to just take a look at the pole positions, like the Formula 1 races, the pole position. And to the right or to the left, whichever you are given, you have to find the time domain signal accordingly. This one, or this one, or this one, or this one. So for two poles, there are 4 possibilities. 3 of them are reasonable. One of them is, of course, corresponding to no region of convergence. Now, before the break again, I will write down a final example. And in this example, the poles will be, unfortunately, complex. because the real poles are quite easy to discover. It's this, x of t is given as e to the minus 2t u of t and plus e to the minus t cosine 3t u of t. Whenever you have an oscillation like this and the damping factor, that's a damping oscillation. You see that? This component. Whenever you have something like that, it means the poles are not on the real axis. In fact, if you write it using the Euler's expansion, it will be e to the minus 2t in a parenthesis. I will multiply everything by a single u of t at the end, plus 1 over 2 e to the minus 1 minus 3j t plus 1 over 2 e to the minus 1 plus 3j t, close the parentheses, u of t. So what did I do? I wrote x of t in the complex exponential form, and since it is multiplying e to the minus t, these two terms will contribute as e to the minus t times e to the minus 3jt plus e to the minus t times e to the plus 3jt, something like that. So this is your thing that you get, and the Laplace transforms of these are, this one is the simplest, it's 1 over s plus 2. What is this? There is a 1 over 2 over what? It's the same. S plus, yeah, whatever this thing is, you have to write it that way, 1 minus 3j. And for this one, it's 1 over 2 over s plus 1 plus 3j. So, where are the poles? By the way, it's this plus this. X of s is the summation. The summation can be simplified, by the way, or put in a more compact form. I'm going to write it, but just for curiosity. 2s squared plus 5s plus 12 over s squared plus 2s plus 10 and s plus 2. Now you see that we are looking at the roots of the denominator, and the roots of the denominator are indicating us that this one has complex roots, and the roots are 1 minus 3j and 1 plus 3j. They always come in conjugate pairs because it's a real polynomial. And there is also another real pole at s is equal to minus 2. There's a root. So when we draw this at s is equal to minus 2, we have a pole. This is one of the poles. Where are the other poles? Minus 1 plus 3j and minus 1 minus 3j. So this is the imaginary axis. And minus 1 is here, plus 3j is here, minus 1 minus 3j is here. So we have 3 poles, and these are in conjugate pairs indicated at minus 1, or the real axis for this one is at minus 1, this one is at minus 2. So what is the region of convergence? How come? It's to the right of minus 2 from here, intersection with, to the right of what? To the right of this point is minus 1. So this means real part of s is greater than minus 2. This means real part of s is greater than minus 1. You are only talking about the real part, okay? The imaginary part doesn't matter. And real part of s is greater than minus 1 again. So what's the intersection? Real part of s is greater than minus 1. This part. Does the region of convergence include any poles? No, it doesn't include any poles. So the positions of the poles are not necessarily on the real axis only. They may be out of the real axis. Wherever they are, the region should avoid it. Now it's a very nice exercise for you until tomorrow to think of again two other possibilities. If you have this as the Laplace transform, think of other possibilities of regions of convergence. What are they? Between -2 and -1 and to the left of -2. For them, what is the corresponding time signal? Can you find it? Yeah. So that's a nice exercise until tomorrow, I guess. We can stop at this point.